Welcome to the Explainer. Today, we are doing a complete teardown of Supabase's high-performance open-source engine. So if you've ever wondered how modern, incredibly scalable backends are constructed completely from the ground up, well, you are in the exact right place. We're going to break down the underlying architecture that allows developers to build everything from real-time multiplayer apps to cutting-edge AI tools. And honestly, what blew my mind researching this was just how cleanly the whole shebang fits together.
Okay, let's dive into this. Right off the bat, we really need to understand how Supabase completely departs from those classic proprietary backend-as-a-service limits. Where a platform like Firebase, for example, kind of locks you into a proprietary NoSQL database, Supabase builds its entire world around open-source tools and standard relational PostgreSQL. This fundamentally matters, because you get the massive scalability required to grow a global app, but with the absolute freedom of open source, meaning you actually own your data structure and you aren't trapped by a single vendor's ecosystem.
So, to make sense of all this tech stack soup, we're going to break it down into 6 highly organized, logical components. First, the Postgres-powered backend. Then, connections and secure authentication. Third, real-time at global scale. Fourth, execution at the edge. Fifth, powering modern AI applications. And finally, taking control with self-hosting. Let's start right at the foundation with part 1, the Postgres-powered backend. Postgres isn't just a database here. It is literally the unabstracted core of this entire ecosystem. The system is built on these strict architectural principles. Everything works in isolation, it's integrated, it's extensible, and it is totally portable. What's absolutely wild is that you can run this entire product with nothing but a Postgres database. Every single integrated tool they add to the stack simply multiplies the system's power without locking you in. And avoiding vendor lock-in, that's a huge deal. It means you never hit that invisible wall where the platform suddenly dictates how you have to build your business.
And this brilliantly illustrates their philosophy, the polyglot tech stack. Supabase didn't just pick one programming language and stubbornly force it to do every single task. No way. They chose the absolute best programming language for each specific job. They use PostgREST, which is written in Haskell, to instantly turn your database into an API. They use GoTrue, written in Go, for lightning-fast authentication. They rely on Elixir to handle those massive WebSocket real-time connections, and Lua for the Kong API gateway. It's honestly a masterclass in utilizing the right tool for the right job, rather than just forcing a single language to do everything poorly.
Moving up the stack, let's tackle part 2, connections and secure authentication.
So how does a system safely handle user access? Authentication in Supabase isn't some mysterious black box. It's powered by GoTrue, which is a dedicated service written in Go. Actually, it was originally a fork from Netlify. It manages your users and issues JWT access tokens. But the real magic here is how it tightly integrates with Postgres's native row-level security. Your user data is stored safely, right there in a hidden Postgres schema, giving you total control and visibility, all without compromising on security.
But, what happens when thousands of those authenticated users hit your database at the exact same time? That's where Supervisor, their built-in connection pooler, comes into play. As a general rule of thumb, if you aren't heavily relying on the PostgREST API, you can allocate 80% of your database's maximum connections directly to the Supervisor pool. This is a crucial best practice. It allows you to handle incredibly high traffic and concurrent connections incredibly efficiently, while purposefully leaving a 20% buffer for your auth server and other administrative utilities, so the whole system stays rock solid.
Now let's look at part 3, real-time at global scale. Think about this for a second. How does a change in a database sitting in Frankfurt instantly reach a user on a mobile phone in Tokyo? It sounds a little bit like magic, but really, it's just brilliant engineering.
Here is the actual mechanical breakdown of that broadcast. First, the system connects directly to a Postgres logical replication slot. Second, it streams the write-ahead log. You can think of this like a running receipt of every single database change. Third, it appends unique Erlang subscription IDs to those records. And finally, the Phoenix Pub subsystem broadcasts those JSON messages out over WebSockets. It operates like a shortest path relay race. The globally distributed Elixir cluster seamlessly routes these messages to subscribers in literally the exact time it takes to ping the cluster. It is wildly efficient.
That brings us to our next layer of compute, part 4, execution at the edge. Sometimes you really need to run compute-heavy tasks, stuff like filtering an uploaded image or handling a custom API webhook, but you definitely don't want to bog down your main database doing it. That's exactly what edge functions are for.
The magic here relies entirely on the Dino runtime. When you deploy a function, the Supabase CLI neatly packs your code and dependencies into a highly compact ES zip file. Then, a global API gateway routes the user's request to the geographical edge node closest to them, making sure that data travels the shortest distance physically possible.
So the crucial point is how these functions actually execute once they hit that edge node. They use V8 isolates. Instead of spinning up a clunky, whole new virtual machine or a container for every single request, an isolate is just a disposable, incredibly lightweight, sandboxed environment with its own memory heap. This means your cold starts happen in mere milliseconds, which, if you've ever sat around waiting for a traditional serverless function to wake up, you know is an absolute game changer. It completely prevents side effects between concurrent requests, keeping your serverless compute insanely fast, cheap, and secure.
Now we get to apply these modular pieces to basically the hottest topic in tech right now. Part 5, powering modern AI applications. What makes Supabase such a powerhouse for modern AI development is that you absolutely do not need a separate, super expensive vector database. Thanks to the PG Vector extension, you get native vector search right inside Postgres. Your embedding vectors, say those 1536-dimensional vectors you get from OpenAI, they live harmoniously in the exact same database as your standard relational data and metadata. You can index them using HNSW for incredibly fast semantic similarity searches, all while still fully respecting your existing row-level security policies.
Let's move to and see how this builds a concrete, buzzword-free architecture for something like a retrieval augmented generation or RAG chatbot. Step 1, your user uploads a document to storage. Step 2, a storage trigger automatically fires off an edge function that securely calls an LLM to create an embedding. Step 3, that shiny new vector is stored right back in pgvector. Step 4, when a user asks a question, you just perform a semantic vector search, blending your keywords and vector similarity to fetch the absolute perfect context. It's an entire end-to-end AI backend pipeline, seamlessly handled by one unified system.
Finally, we arrive at part 6, taking control with self-hosting. The ultimate freedom of this entire ecosystem is portability. Their product principles actually state it perfectly. To avoid lock-in, we make it easy to migrate in and out. Because every single piece of this stack is completely open source. From the Postgres core right up to the GoTrue Auth and the Elixir real-time cluster, your data is never trapped. You can literally just take the keys, download their Docker Compose files, and run the whole stack yourself if you want to. But I do want to remind you, with great power comes great responsibility, right? If you choose to self-host, you are taking on absolutely everything the cloud usually handles for you behind the scenes. You suddenly become responsible for server maintenance, operating system security updates, ensuring high availability, and of course, managing those dreaded 3 a.m. database backups. It is a serious undertaking for sure, but for enterprises with strict compliance needs, having this option is a massive game changer. What's truly incredible about everything we've just unpacked today is the sheer potential it represents. We've looked at an architecture that scales globally, processes real-time data in milliseconds, natively understands AI embeddings, and on top of it all is completely open source. So I want to leave you with this question. With an open source engine this powerful, what is stopping you from building the next massive AI app right on your own hardware? I hope this explainer has left you inspired and eager to start building. Thanks for hanging out with us, and we'll see you in the next one.